Hi, my name is Jeremy Boyle, and today I'll be presenting the first update on my research project from this summer. This project is called Creating a Workflow for Identifying and Analyzing Variants of Compressive and Tensile Properties in a Hyperelastic Material. I'm a student at the University of Texas at Austin. This project is a collaboration between Los Alamos National Laboratory and also is supported by Texas A&M Department of Material Science Engineering REU program, the Research Experience for Undergraduates. My mentor in this is Thomas Thompson from the Los Alamos National Laboratory. One of the first issues that you always run into when you're trying to characterize a hyperelastic material. Now, a hyperelastic material is like a rubber essentially. It's very elastic. Again, the issue you run into is that unlike most materials, their stress-strain curve is not linear in the first part of it, which in most materials follow Hooke's law, obviously, and it's not doing that. And so there's no the elastic modulus is a tough metric to use here. They also, like many materials, they're varying. Their properties vary based on the test conditions, temperature, stress rate, load rate, things like that. And so we have access to a lot of test data, and our objective really here is to develop a process using rigorous statistical methods and also grounding it based on material science in how should we analyze hyperelastic material test data in all these conditions to properly characterize them, to allow better modeling of them, and also to provide feedback for the material manufacturing process so they can reduce the amount of variance in the material properties and just improve the process overall. Next, I'll try to really speed through the methods of how we're going to be making this process and analyzing these with rigor. And first step is that we need a scalar to compare these, right? In lieu of elastic modulus, which again we can't easily get because it's nonlinear. So we need to find a scalar for each of these tests to be able to compare them and say, look, these scalars are significantly different based on these conditions. And that's where analysis of variance comes in. So variance such as batch and temperature of the test, how it was made, the load direction is also one we're going to look at. And then, of course, we have covariates too, which adds another mix to the level. So these are continuous variates, soak time, and humidity that are going to add this level of analysis of variance. And this will all bring us to hopefully this end goal of having this whole process laid out. And this process, again, gets us to material property trends, recommendations for future tests, and also the process feedback and information for the designers. Next, let's cover concretely our preliminary results. So when I say we, I mean my mentor and I. So one of the first things that we did is we reviewed some models for hyperelastic materials as again, they're nonlinear, so there needs to be a more complex equation for them. And we were able to find some and fit them to the data. That was a challenge of learning MATLAB methods for curve fitting and representing equations, and also doing work in data management, getting that data in forms that are going to make it really simple to analyze it, to run various statistical checks on it, and run them through statistical tests, so ANOVA, analysis of variance. And those are some of our next steps, right? Our next steps are going to be working with more than just this inflection point that we found on the graph there, but looking at next steps such as tangent modulus, pseudo toughness, also looking at covariate analysis at our covariates such as soak time and humidity, as I mentioned before, diving into these tests really head on now that we have the data set up, and also diving into more tests besides just right now we're just looking at tension, just pulling it apart, but we want to eventually look at the methods for interactions when it's being compressed together. So a lot of work ahead of us, and I'm really excited about that.